This is the Lecture 6 Q&A, and there's a new feature. In the description of this video, there are timestamps and brief descriptions of each question that was asked, so that if you want, you can jump around. Yeah, so the question was about lecture. We thought about what's actually important for some square to know about square in order to use it correctly. We decided that its behavior was important, the number of arguments that it took was important, how it was implemented was not important, and there was this one detail about its intrinsic name. I said that's not important. The question was, what is an intrinsic name anyway, and why doesn't some squares care? Some squares really does care how it can refer to the square function, and it's going to refer to it using the name square. But it turns out that this function that squares things wasn't originally called square in this example. It was called f. Now we also gave it the name square, and so we can refer to it as square out here or within the body of some squares. So we call some squares. Some squares knows that square squares things, and therefore it will compute the sum of the squares of 3 and 4, which is 25. The intrinsic name of this function, which is called square, is actually f. F is the intrinsic name because it's part of how the value is displayed. And it's just the name that the function had when it was created. That's what an intrinsic name is. It's really like an unimportant detail. It does exist in the Python interpreter, so we mention it once in a while. But it's not something that ever matters for the execution of code. It just it affects the output a little bit.
Yeah, so the distinction here is, of course, it needs to know the function name. It's going to call the function, but it doesn't need to know what's happening behind the scenes. It doesn't need to know whether it's the built-in Python function or you've redefined it as f or anything else. That's completely irrelevant to it. It just needs to know, how do I refer to this function to call it? And the fact that there's this name underneath the cover, who cares? Yeah, exactly. In fact, not only does Python not care, you don't, well, you definitely don't care about that. It's not a very important concept. So this is a question about floating point error, if you can call it that. So this is a pesky thing about representing numbers in a computer with finite memory. Yeah, is that when you do floating point calculations, that is when you divide one non-integer by another integer, and you don't use the integer division, the double slash, you don't convert to an integer, you can get, these tiny, tiny, tiny little values at the very end. And where they come to bite you is where you ask things like, if the result of this calculation is equal to 50, then do this, right? Where your expectation of, for example, the division of two values should give you the integer, and then there's this dot 0.0000003, and the conditional doesn't work. So as a general rule, you should not do tests for equality against floating point numbers. And exactly for this reason, and the reason is it's not a bug in your code, it's the way floating point numbers are represented and managed in a computer with finite memory. And so the right way to do that is either you do integer division, and so you're guaranteed to get an integer back. You explicitly cast your result to an integer using the int operator, or you do an inequality. You say, if it's less than 50, for example, or less than or equal to 50, although it depends on the logic of your code whether that will work or not. So I don't know if I answered the question. Maybe John, I think John maybe wanted to chime in too.
I thought that was a great answer. So like a computer can't represent pi because as like a numerical expansion because it goes on forever. And so you're stuck approximating that. It turns out you're stuck approximating a lot of other things if you want your code to run fast. So even rational numbers that you could imagine representing exactly as like a fraction oftentimes are represented based on like an approximate numerical expansion, kind of like this. And there's, the question is like, could you make this go away? And the answer is no. It's baked into the programming language. It's baked into, in fact, all programming languages. The way in which fraction is converted into an approximate decimal expansion isn't something that's particular to Python. It's a standard that's used across basically all programming languages called the floating point standard, and invented by a Berkeley professor, in fact. Well, I guess it was a collaboration, but he got the Turing Award for it. So I think that it's just something that, like, with experience, you can learn how to manage this. There are lots of solutions, but the basic idea is don't trust the last few digits of any large numerical computation. If you're like manipulating a few numbers together, then usually you see errors only in the last digit or the last two. But if you do some massive computation that involves like multiplying and exponentiating tons of numbers and then combining them together, then you can lose quite a bit of precision. And it turns out that even though Python or some other programming language will show you these 15 significant digits, some of them just won't be right mathematically. And that's a compromise we make for having computers be really fast and able to carry out these massive computations. So if you want things to be exact, work with the integers, just like Hani said. If you're not working with integers, if you're working with these approximations, then just accept that like equality checks often aren't the right thing to do.
Yeah, so this is really where it comes. I mean, it come to bite you in a couple places, but equality checks is really where you have to be very careful. So as I said, one way to do it is if you're dealing with integers, do integer division, or cast explicitly do an integer. Now, you may say, well, look, I want like the first 2 decimal points, but not the 20th decimal point. Yeah, because as John said, you don't trust all the way those really, really tiny numbers. So one way to deal with that is you can multiply your number by, say, 1,000, round the result, and then divide by 1,000. So what happens there? If I multiply by 1,000, I get the first 3 decimal points that were first 3 values that were to the right of the decimal point are now to the left. Yeah, and then when I round, I get rid of all the small numbers. And when I divide by 1,000, I push them back into where the decimal is. So that way I can decide, here's how many values I want.
It turns out round will do this for you too. So yeah, I mean, but it is definitely frustrating to see like how come this isn't true. It's so obviously true. But the reason it isn't true is that it does go through the same procedure all the time of like evaluate the left, evaluate the right, and you get different values because of this rounding error. If instead you had rounded these, like Hani said, to 3 decimal points, then you get the same answer there as you do there. And so these two are, in fact, equal. Good approach. Yeah, good question. So yeah, so I guess the follow-up is like, what happens if you're not controlling the equality, but instead like, okay, pi is running this. And so if you return like 50.00003 and it expects 50.0 and it tells you you're wrong, what are you supposed to be able to do about that? And yeah, I mean, that is kind of like a course-specific annoyance. But it also shows up in real programs where you do have to think about, like, is the implementation that I'm going to come up with going to give, like, the right integer output, or is it going to give a rounded version? And this is not really a topic for this course, so I think it's more of just like a course annoyance in this case than it is like something that you should really worry about. And so sorry that happened to you. But eventually, especially in 61C, you really do have to start planning for the kinds of approximation and rounding errors that pop up in real programs and kind of be defensive about them. So yeah, so like you don't want to subtract one number that's really close to 1 from another number that's really close to 1, because it tends to give you like bad approximation errors. So yeah, eventually you got to worry about this. I wish you didn't have to worry about it like in the first 3 weeks of 61A, but sometimes it pops up just because the software isn't perfect.
Yeah. And I'll add one last thing is in numerical methods, this is a real issue dealing with, and John had exactly the right word, is defense. Is that you have to think about, are my numbers going to be really small? Are my numbers going to be really big? Am I going to reach instabilities? And so when you're doing these complex calculations, you do have to worry about these things. I agree in this particular instance, it's just something stupid that happened and we just need to fix it. So I wouldn't worry too much about it right now.
Yeah, okay, so the question is on an exam, for example, if someone gives you an environment diagram and says, what code generated this? How could you answer such a question? Because going the other way is straightforward. You just apply all the rules and you get the environment diagram. But going backwards, it seems like there's no way to determine what the code is just by looking at the environment diagram. And so what are you supposed to do? I think that's true, that there isn't like a clear procedure. anymore. For this reason, if you take an old question on an exam with like a complicated environment diagram and you cover up the code and you try to write that code, it's basically extremely difficult or impossible to do, especially under time control. So all the kind of old examples that you see of environment diagrams are probably just like more complex than you would ever see in a reverse environment diagram problem, meaning one where you start with a diagram and you try to write the code.
And there's almost certainly ambiguities. I mean, there's almost certainly certain environments where you could have gotten there many different ways, in which case we certainly can't say, well, that's not what we were thinking about. That would be weird.
Yeah, so but if you think of simple examples, you see something like, I guess I can't draw it without showing you the code, but like, you see something like, oh, I can do this. What goes here? And the diagram is
John is now hacking the HTML code for the Python tutor so he can create an environment.
Yeah, so if you have like this and you're like, what happened? Or then like, it seems like, well, X had to change. So you can kind of look and see like, oh, if I had run this without this line, then X would have been 2, but X is not 2, so why is that? So it must be that X was changing here. And in fact, there's like enough information here that if we blanked this out, you could still sort of work it out. Oh, it's going to get mad.
But you couldn't do it unambiguously. Like X could have changed to 4 in an infinite number of different ways. The only thing you can say is X has been reassigned at that point. Right? We can't hold you to what expression were we thinking about that changes X to 4?
Right. So if you did anything, yeah, it would be fine to write X equals 4 or X equals 1 plus 1 plus 1 plus 1 or whatever. And in cases where like it's unreasonable that you would kind of figure it out entirely, you might see multiple choices, and then you'd have to consider like, oh, which one of these does the right thing. So yeah, so I'd say it's a slightly different skill to kind of reason backwards. Probably not my first choice of how I'd ask these questions, except for that we live in this pandemic world where we have to come up with the best substitute we can come up with. Yeah, so the right way to approach it is to apply the rules you know to the code that's there, and then kind of hypothesize what could go in the blank that would make the environment diagram actually match the code. So basically, like what needs to change about the code in order to have it appear as the diagram needs. And we'll try to keep the example simple enough that we can test that you know the rules without making you like try 1,000 different things and figure out which one will work.
By the way, is it just me or does the world look like it's coming to the end here in Berkeley?
It is quite plausibly the very last Q&A we will ever do.
I mean, that's not it's like 8:30 in the morning. That's not a virtual background. That's what the outside looks like right now.
Yeah. It's crazy.
Jesus. I've been waiting for it to get normal and it hasn't. So anyway, I'm just saying we have bigger problems than environment diagrams is all I'm saying.
Yes, the real environment is the bigger problem than the environment.
The real environment. Okay, sorry, let's get back on track.
Okay, so the question was, what's going on with the environment diagram for this, which says that f is a function that takes x, returns a function which takes y, which returns a function that takes z, and finally does some work. It calls g on x plus y plus z. Okay, so what's g? G is not f, but instead the result of calling f. So that means that x already has a value, which is 3, but y and z do not. So in order to make progress, we would have to take this result, g, and call it. But that's actually not what we do in this environment diagram. Instead, we ignore g completely. So g just kind of hangs out there, and we call f. Every time you call f, you're going to get a new f frame where x is bound to something else. So here, x is going to be bound to 4 and return a function. So let me just go back here. This is going to give you back a function that takes y and does some work. This is going to give you back a function that takes z and does some work. And this is going to give you back a number, the result of calling g on x plus y plus z. Well, we do eventually call g. That's good. Okay. And what does g give you back? Well, we'll find in a moment that it is going to give you back a function that we never bother to call. Should we have it like finally resolve? Let's add a little bit to this. It'd be so nice.
Yeah, let's
Z equals, we'll call g, oh, we need to give this a name, h, and then we'll finally call h on something, 7. Okay. So let's dive in. F is a function. Notice that this was just one step. We evaluated this lambda expression, which made a lambda function. But since we've never called it, everything after the colon doesn't really matter yet. But it does have a name because we used an assignment statement. Now we do call it. So we get a lambda frame. The way we create this frame is to copy over the name of the function, copy over the parent, copy over the formal parameter, and then what's the argument? Well, whatever we passed in, which in this case was 3. And what does it do? Well, this is a function that takes x, which we've done, and returns a function that takes y. So you're going to see a return value, a function that takes y. Now we're done with that. We now know what the expression f of 3 is equal to. It's equal to this function. And now we have to do the assignment. So g equals, this is a global assignment statement. It's not part of the body of any function. And so g is assigned in the global frame. Okay, now for the part where we call f again. When we call f on, well, when you have this like nested expression, you really have to figure out what you're calling. And so in order to figure out what you're calling, you have to evaluate f4, 5. But to do that, you have to figure out what you're calling for that sub-expression, which is f4. Figure out what we're calling there, it's f. That part's easy. But calling f of 4 gives us the function that we will call on 5. And that will give us the function that we call on 6. So first we have to call f on 4. Now what is f? F is this lambda function, which we've just called. We've bound its formal parameter x to its argument 4. And now we return a function, just like we did before, except for this function is different. It's got the same code, except for it's got a different parent, and therefore a different x value. This has an x value of 4. So where does this get returned? This is the function that we're going to call on 5. So this function that we just returned is going to be called on 5. This function takes y, and so we see we've taken y, we've bound it to 5. And what does it return? It returns a function that takes z and does some work. So we're going to see a return value of a function. The function that takes z, and its parent is the f3 frame, which is where this lambda function was created. Whew. What do we do with this? Well, now we figured out what f of 4, 5 is. And we have to call that on 6. So we're going to take this function right here, bind z to 6 in a new frame. There it is. And then we look at what this does. Well, this calls g on x plus y plus z. So before we can call g, we have to figure out what x plus y plus z is. And here things get a little bit interesting. So we look up x. It's not here, so we look in the parent, which is the f3 frame. There's no x there, so we look in its parent, which is the f2 frame. And there finally we found an x, so x is 4. Now we have to figure out what y is. We look here, there's no y, so we look in its parent, there's y is 5. And we look for z. Z is right here in the local frame. So we add 4, 5, and 6 together to get 15. But we don't return 15. We assign y to 15 in a new frame because we have called g on x plus y plus z, which was 15. So we computed all that 15 back when we were like here, right? In order to figure out what g of x plus y plus z was. We computed the 15. We looked up the g. There was no g here, no g here, no g here, and we found the g. But then what we do with the 15 is we pass it in as an argument to the function, which is this lambda called g. Introduce a new lambda frame whose formal parameter is y. Y is bound to the 15 that we computed already. And now we figure out what to do. Well, it's this function. So what we do is everything after the colon. We evaluate lambda z, g, x plus y plus z. Oh, this is never going to end. That's annoying.
yeah.
So maybe we'll forget line 5 and just kind of finish with this. This is a nasty environment diagram, isn't it?
Yeah.
We're almost done, though. So we've called g. And what does g do? It returns a new function. So there's a new function that we return. And we return it to here. We needed a return value for f4. We never got that. it just returns whatever G returns, because it says return whatever G returns. And so this function will be the same return value for F4 as it was for F5, and will eventually be bound to H in the global frame. And let's forget this line. Okay, so we did draw this. Now we can comment about how atrocious it is.
Yeah, so a couple of things about this. You should never, ever write code that looks like this. This is absurd. The only reason you do this is for pedagogical reasons, to make sure you can, do sort of the backflips to do this. But this is an absurd example. Nobody would ever write code that's this obfuscated or complex. It would serve no purpose at all. So it's a fine exercise for being able to step through these environments, but I don't think if you wrote this kind of code, your manager would yell at you.
Yeah, exactly. Writing the environment diagram, it does tell you exactly what's going on. Following the parents does tell you exactly what X and Y and Z are equal to. If you were actually trying to analyze this code, I'm not sure that drawing an environment diagram is the first step. I think the first step is to try to read it and understand what it might do. And then the environment diagrams could help you verify that. So what this might do is take X and Y and Z in sequence in like a call expression like this, and then return the result of adding all those together and calling G, whatever G is. Okay, so what makes this example particularly diabolical is that G is just like some other function that returns a function and it never does anything useful. Pretty sure I didn't write this problem. But anyway, the story there is like, once you know that this is going to take 3 arguments and add them together, then you can kind of check to make sure that things went right in your environment diagram by seeing like, oh, here was this moment where I took these 3 things and I added them together and I got 15. So that's good. That means that like I haven't kind of screwed up my steps along the way. Did you have follow-up questions about this example?
I think I got it. I was just like kind of confused about like the last bit that you explained, like what G's purpose is and like what it actually like returns in the end. But I think it's good now. I just had like another question on a different problem. This one's from like a past exam. Should I share my screen or should I just like type the question number?
Yeah, why don't you just tell us where to find it?
All right, sure. It was question 2 from the summer 2019 midterm one.
Oh, summer midterms, okay. This one, correct?
Yeah. With this one, like in the last, in frame 4, like I think you call a function that uses a variable called ice, and ice has like 2 different values. There's one in the local frame and one in the global frame. And I wasn't sure which one you use and why, so yeah.
The next question was how to solve an environment diagram problem from the summer 2019 midterm, question number 2. All right, let's take a look at this really quickly. So it says define view, which is done for us, define review, which is done for us, assign ice in the global frame. Now we're going to assign read in the global frame, but we can't really do that until we figure out what view returns. So before we can call it, we have to figure out what argument it's going to take. Evaluating this lambda expression just creates a new function of PR, whose parent is global. Okay, so now that that's created, we could try to call view. View is a global function. Sorry, I've never really tried to use these zoom annotators before, but it seems like it's working okay. View takes an argument called RE, and what is that argument? It's oh, maybe I can draw an arrow. Bingo. It's this function. And then we have to do a little bit of work to bind ice to 4. And then we define a new function called k. K is a function. Sorry, there's a lot of clicking involved. Whose parent is the F1 frame. That's where we are right now. Put another arrow. And what do we do with this? Do we call it? No, we just return it. So since we return it, that means that's the value of view called, and therefore we're assigning that to RE. Finally, we call review on 1. So that means we need to introduce a review frame. Review has a formal parameter PR bound to 1. It can't return for a while because we have to figure out what the result is of calling RE on PR times 2. Okay, so first step is to look up which RE. The answer is you look here. Since there's no RE, you look in the parent. And you call this one. Okay, so we're calling the k-means function. What are we calling it on? PR times 2, well, that's easy. PR is 1, so we're going to call it on 2. Okay, and close, folks. K is, this new frame has name k. It's got parent F1. I just read that off of the function that I'm calling. And it's got formal parameter name means. Oh, close enough. Which is bound to 2. That's the PR times 2 that we already calculated. So what happens when we do this? Well, we have to return the result of calling RE on means. Means is 2. That part is easy. What's RE? Well, we look here. There isn't one. So we look at its parent, and it is this lambda function. Finally getting to your question, I think. Okay, so we call that lambda function by writing down its name and its parent, binding its formal parameter to its argument. So what did we call it on? We called it on means, which was 2. And then we have to finally execute its body, which is PR times ice. So we look for PR, it's here. We look for ice, we look here, there's no ice, so we look in the parent, G, ice is 3, and we add 2, or we multiply 2 times 3 together to get 6. So since the value of this is 6, that means the value of this is 6, which means that's the value of this is 6, and we made it. So the reason, even though there were 2 ices, and this one was kind of closer than this one, that we used the one out here, is that this lambda function was created in the global frame because we evaluated this lambda expression before we ever called view.
And as John was saying earlier, the environment diagram is a really good way of just very formally going through that. But if you just look at the code, you can sort of see that, right? You can see that in the global frame, ice is set to 3. So when you call view with that lambda expression right there, that ice is going to be set to 3. You can see that it's going to have to use that global value as well.
Exactly. So in any line of code that's not indented, that's just part of the global environment or executed in the global environment, you're basically just saying like, oh, I'm making a function that multiplies things by 3. If ice changed later, then it would be more complicated, but ice is not changing. So this is just like a function that multiplies by 3. So whatever happens, you want to make sure that you multiply by 3 at some point, and we finally did. And so that's kind of like a nice check that we did something right.
Again, nobody would write code like this. This is a pedagogical thing, so don't think that this is what the world of coding is going to look like for you. This is pretty cryptic. But it's a good exercise to make sure you can sort of follow the logic of these things.
Okay, so great question. The question is like, how do you know what's allowed and what's not allowed? Like what's going to work and what's not going to work? And in particular, the reference was to the example from today's lecture where we passed Mario at into both. And Mario at was this like very complicated thing that played the Mario theme song at a particular octave. And what was the Mario theme song? Well, that was defined by an even more complicated thing that was like do 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 or whatever. So there's no restrictions on what functions you can pass in as an argument to anything. In Python, and other programming languages tend to work like this too. If it's the case that in your programming language you can pass functions around, then typically you can pass any function as an argument. Now, your code is only going to work if you're passing the right kind of argument into a particular function. And what kind of argument works really depends on how the function is implemented, what the function does. So the part of this example that does all the work is this play function, which does something I didn't even really describe very well. Like creates this wave file using a bunch of built-in encodings or whatever. But it takes a function, and this is the one that we built, the function that plays the song. It can't be just any function. It has to be a function that takes in times and gives you back wave heights. Otherwise, something's going to break. So every time a function takes another function as an argument, you have to know something about that function. What kinds of arguments does this one take, and what's it going to return? Then you can start doing interesting stuff. If you just say, if you just pass the absolute value function in here, I guess surprisingly that would work. But if you, if you pass make getter in here, then you'd run into all kinds of trouble. So Python's not going to complain if you pass in any old function, but your code's not going to run unless you pass in the right kind of function that has the right kind of behavior. So this has to be a function that takes in positive integers and gives you back the sampled wave amplitude at that time. Okay, so
John said something important that I just want to emphasize this again too, is that there's sort of two types of problems you can run into in coding. One is you go to run it and Python says something's wrong. You did pass the wrong parameter, something happened, and it sort of catches the mistake for you. When you pass a function in and you tell the user, look, this function must take as input a single parameter time and return the samples, Python's not going to check that for you. That's on you. So it'll run, and then you'll have a problem downstream. So that in that regard, by the way, it won't even know if you're passing in a number until it goes to try to evaluate it. So there's no way of knowing until you actually run the code, and that's on you, the programmer, to make sure you're passing the right thing, and Python won't check for you.
Yeah, exactly.
That's not true of all languages. Some languages are a little bit smarter about these things.
Yeah, some languages you have to kind of say what you want in advance, and then it will check it for you in different ways. You'll do a lot of that in 61B, actually. So, so the design of the rest of this program was just about making sure that you're building functions that behave in this way, that take in one argument and return one number. And we did that when we were just creating a basic waveform, a triangle wave. We did that when we created both, which was basically if a number comes in and I have two other functions that I can pass this number to, and I get two different wave heights, then I could just add them together, and then I get kind of both waves happening at the same time. And that means I could pass that kind of thing into play. Same story with note, is we made sure that the function we returned was the right kind of function to pass into play. And we even did this for Mario. So it turns out that Mario was a function that returns a function which was the same kind of thing that note was, or the result of both was, because it was just built out of a bunch of boths and notes in the first place. And so what we got was a function that we could pass into play. And Mario@ kind of did the same thing. It returned the result of Mario, which was the result of both, which was the result of note. And what's note anyway? Well, note is one of these functions where you take in how far into the song you are, and it returns what the height of the sound wave is at that time.
By the
So,
way, many years ago when I was first taught how to program, I had a professor who insisted that you call functions with more information than just a name. So it'd be like, this is an integer, and you'd put the word int in the variable name. Or if it was a function that takes one parameter and returns a parameter, there's a notation for that, so that in the function name or variable name, there's all this information about the type. I'm not necessarily recommending that. But when you just have some generic name, you don't know unless you go look at the code, see what it does, and then make sure. So there are mechanisms you can do in just the naming convention to sort of help protect yourself downstream.
and I think the most obvious example of where this can go wrong is if you have some, so what I have is a function that calls f on the result of calling f on x. And here's just an example from some lecture recently, I think. Or maybe it's from Friday's lecture, I don't know. But I think we did this already. Okay, so, and what happens when you square? You just square it. So if I make g is twice square, I've done all this complicated stuff, but I have kind of followed the contract, which is that twice takes in a function that you call on just one argument. And I've taken a function that you call on just one argument and passed it in. So if I square 3 to get 9 and then square that to get 81, everything works and nothing crashed. But if I tried to twice pow, since pow is a function that takes 2 arguments, I'm going to run into trouble. And it won't tell me I ran into trouble when I call twice. It'll only tell me I ran into trouble when I actually try to do some work by calling h. So what h does is h is this function, which was supposed to take one argument, and we gave it one argument, and then it was supposed to call pow on that one argument, but it turns out that pow, which is the function that raises one number to the power of the other, requires 2 arguments. It can't do anything with just one. If you call pow on 3, then it gives you this same error. So one of the standard contracts that you have to kind of obey is that when you're passing in a function and you're going to call that function, then you better pass in the function that takes the right number of arguments. And there are lots of programming languages that force you to annotate this, or you could try to put it in the name somehow, or you could just know. I mean, when the code is this simple, then it's kind of obvious. But in more complicated examples, you'd want to put it in the documentation somewhere. The next question was, what happens in an environment diagram when you have an outer function return an inner function, and the inner function returns the outer function? How does that work? If I were to call f on 2, I would get back a g function which takes y. So I could call that on 3, which would give me back the same old f function that I had before, which I could call. It should give me back another g function, which I could call that. So what's going to happen here is that we'll get just one f, but 2 different g's. The first g is created the first time that f was called. And what's special about it is that its x, if it used x anywhere, will be bound to 2. So maybe to make this slightly more interesting, we should use x somehow. Z equals x. Or how about negative x, so we can see the difference. Okay, so we called f, which created a g function, which we haven't called yet, but we will eventually, because we're going to return that. So that's the value of f of 2, and we're going to call it on 3. So when we call g on 3, we get its formal parameter y bound to its argument 3. And then we actually execute its body, which in this case is to look up what x is. So we look here, there's no x, but there it is, and we get z is bound to negative 2. The assignment is always local. It's always in the current frame. And then we return f. So what does it mean to return f? Well, you look here, there's no f. So you look here, there's no f. So you look here, oh, there's an f. So we're just returning a reference to this function, meaning that's what we're going to call on 4. Is we're going to call the same old f that we had before. When you call f twice, you create 2 different g's. And that's important because each g is going to behave differently. Even though it has the same code, it's going to have a different x. And that's represented by the parent. So the next g, when we call it on 5, we're going to bind y to 5. So that's one thing that's different, is that it was called on a different argument. But the other thing that's different, which has nothing to do with y, is that its x is in the F3 frame instead of the F1 frame. And so its x is bound to is bound to 4. So when we say z equals negative x, then we get z is bound to negative 4. And what does it actually do? Well, it doesn't do anything with z. It just returns f yet again. So, outer functions, you just execute the def once. There's just one f function. Even if you return it many times, there's still only one f function. Inner functions are different. Every time you execute f, you're going to get a new g with a new parent. And so in this case, we're returning a different g every time we call f. We called f twice, so we got 2 different g's.
The other way to think about this is forget about an inner def. Every time, if I just have a function f and I declare a local variable in there, z is equal to whatever, then every time I call that function, I get a new little local variable. So every time you call that function, frame gets created, everything gets evaluated within that frame, whether it's a function definition, a variable definition, it doesn't matter. Yeah.
The next question didn't actually get asked in the Q&A session, but someone did ask me in office hours yesterday, and so I thought I'd answer it here. And the question was, what's going on with Hog question 7, implementing announce highest? How are we supposed to know how to start, and how is this going to work? And there's a very nice walkthrough video about this already that's linked from the Hog project, so maybe just watch that. But here's my take, is that announce highest is just like a function that's provided to you called announce lead changes. So let me talk a little bit about how this works, and then you can imagine altering it to implement announce highest. This is a higher order function that returns a say function. If you've gotten this far in the project, you know a say function is a function that's called on the scores after every turn. It might print something out about what's going on in the game, and then it also returns a new say function. Now the funny thing about this example is that this doesn't say return say. It says return announce lead changes leader, but announce lead changes does return say. So this complicated expression is very similar to just writing return say. But there is a difference. Instead of returning this say that just got called, it returns a new say with the same code, so the same behavior, but a different parent frame, one that was created with a different last leader. So what this announce lead changes function does is it creates a say function, here we've created it by calling it, that knows who was winning before. It gets in new scores and figures out whether who's winning now is different from who was winning before. Before, no one was winning at the beginning of the game. Now player 0 is winning, and so it prints that out. But it also creates a new function that knows who was winning now. Now player 0 is winning. So when I call F1, if player 0 is still winning, there's nothing to report. But here, player 1 is winning, has a higher score than player 0, so it prints something out and returns a say function where player 1 is winning. Call this on the new scores, player 1 still winning, nothing to print. So in this version, player 1 still winning. Call that, player 1 still winning, nothing to report, and in this one, player 1 still winning. We call that, and since this function knows player 1 was winning, but now we observe that player 0 is winning, it's time to print something out. And then this function, which would be called on a subsequent turn, would know that player 0 was winning just before. So what's interesting here is that we have the behavior, which is print out when somebody new is winning. And also some information. Who was winning already before the new set of scores came in. So the new set of scores come in here, but who was winning before is stored here. And all three of these names are available in the body of say. This default value is just indicating that at the beginning of the game, nobody's winning. But every time announce lead changes is called in the future, we will pass in either 0, 1, or none to indicate who was winning at the end of the last turn. And that's what all this logic is about. It's looking at the two scores to figure out who's winning now. Then it does a check. If it turns out that somebody's winning and it's different from who was leading before, then print out that the lead changed. And finally, return say, but not the same say, a new say with a new last leader. Every time you call a function, you're assigning its formal parameter to some argument. So we've computed the new leader based on the latest scores, and we pass that in as the last leader in order to get a say function that when it gets even newer scores, it knows who was winning last turn. What's nice about this design is that this function can keep track of exactly what it needs to keep track of and nothing else. And it doesn't need to know anything about the rules of Hog. It just knows that scores change, and sometimes it's time to print out when something interesting happened. So if we scroll down to announce highest, this keeps track of more stuff, because announcing when somebody got the highest score they've ever gotten in the whole game requires a little bit more information. You need to know who you're talking about. In this version of announce highest, who always stays the same. You say, I only care about player 1, and then that never changes. And then you keep track of what score did player 1 have the previous turn, because you want to figure out how much they gained. You only get their total score, so you have to subtract. And you also need to know what was the highest score they ever got in any turn before. This is a fact about the whole game that needs to be tracked over time. When you call announce highest on player 1, then this function knows it's about player 1 whose last score was 0 and has never scored more than 0 points. Now, when player 0 gets 12 points, player 1 hasn't gotten any points still, nothing really changes. But now player 1 gets some points. 9 minus 0 is 9 points. So that gets printed out. That's the most that player 1's ever gotten. And a new function is created that knows once upon a time player 1 got 9 points. And also, last turn they had 9. So next time around, they have 9 still. They've gained 0 points. That's not exciting. But the next turn after that, they've gotten 30 points total. That means the points they must have gotten over the last turn is 30 minus 9 is 21. And 21 is bigger than 9, which is the most that we've ever seen before. And so something gets printed out. Which means that F4 remembers 3 things. We're talking about player 1. The last score they had was 30. And their running high was 21. That's the most they've ever seen. We call that on some new scores and see that player 1 just got 17 points, which is not as much as 21, so we don't print. Then player 0 gets to go, then player 1 gets to go again, and here they got 30 points. 77 minus 47 is 30. So this function had to know that the last turn they had 47, so that they can compute 77 minus 47. It also needs to remember that the biggest turn score ever seen for player 1 was 21. We have enough names to track all that stuff, and so we can write a function with exactly the same structure as announce lead changes. Define say, a function of score 0 and score 1, that computes interesting stuff about the current score. This interesting stuff will have to be different in announce highest than it was in announce lead changes, because we don't care about the leader. What we care about is how many points player 1 or player 0 got. Then we'll have some if statement to figure out whether it's time to print, and then we'll call announce highest with new values. Who stays the same. The total score at the end of the last turn will change. And the running high, the highest score that this player has ever gotten in a single turn, might change too, if they just reach the highest score ever on this turn. Otherwise, it will stay the same. I hope that's a helpful orientation about how to approach question 7.